Broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone, and welcome to the next in our webinar series that we're running in conjunction with GenLess. Today, we have YEH with us, and representing them is Yariv. Yariv is expert in renewables, especially solar, but overall renewables he has covered off pretty well as well on top of that. So I won't hold you up too long. There is a little bit of housekeeping that we have to do, and that relates to how we deal with questions. So part of our webinar package means, and we have to do this simply on the grounds that if we don't, we get too much background noise and feedback. But all attendees at the moment are defaulted to have their microphones switched off. And so we pretty much have to run it that way with 192 registrations that we have today, which is excellent result, and it just reflects how significant and important renewables are likely to be for us in the next few years. So you're all on mute by default. The way we'd like to deal with questions today is that if you could type in your question to the little dialog box that you should see on the right-hand side of your screen, or later on, especially when we get to the question and answer session, you can raise your hand. You should see a little icon available again in that dialog box, which will allow you to raise your hand. I shall be monitoring those questions and hands up as we go through the program. And what we'll do later on in the session when Yariv is finished is that I will open up the microphones of those individual questioners, so that they will be able to ask those questions in person and engage in a dialogue if there are any follow-on questions arising from the answer. So I think that's enough from me. What I'm going to do now is hand you over to Yariv. So Yariv, you have control of the screen. If you'd like to switch on your webcam, there you go. And you have control to put up your slides as well. So if you haven't met before, everyone, this is Yariv.
Hello.
Sure, he can introduce himself. He's highly experienced in many of these things. I'll confess he did give me a little description about his background, but I'm sure he's much better placed to describe that than I am in his experiences. So over to you, Yariv, and I'll keep a lookout for the questions as they come in.
Thanks, Mike. Thank you for the introduction. And hello, everyone. Thank you for logging into this afternoon webinar about making on-site, commercial on-site renewables work for your business. Let me just share the screen. Can you see the screen, Mike?
Yeah, that's all good. I'd muted myself. Sorry, that's all good, Yariv. Coming through loud and clear.
Right. Okay. Yeah. As I mentioned, I'll be talking about making on-site renewables work for commercial building today. The topics for today's webinar briefly will be key market drivers for commercial on-site renewables, the methodology that we take on our projects, project feasibility. We look at projects from a physical, technical, and environmental standpoint. The financial business case, and we'll touch a little bit of some financing models that are available. The engineering and design of a system, the procurement of the goods, and the construction of the system. And of course, once the system is installed, we would like to monitor it and operate and maintain it. If we do have time, I'll touch a little bit in microgrids and virtual power plants as part of power sharing, but we'll see how we go. Just a couple of words about YEH Renewable Energy Solutions. We are independent consultants providing technical and financial advice on clear power generation, microgrids, power sharing platforms, and of course, engineering design services of renewable energy systems and cogeneration plants. We typically provide frontline services to private companies, municipal, government, and public development companies. And we also provide backline services to industry partners like solar companies or EPCs, project management companies, architectural designers, and of course engineering companies that we work with. The reports we produce are typically aimed to provide executives, company executives, decision makers, financial control teams about project profitability without the need to have an in-depth understanding of energy generation and energy consumption. In order for us to deliver bankable solutions to our clients, we try to understand what the electricity consumption and the power demand in a proposed site are, and how the billing and metering and the network are going to be structured. For most cases, we also identify possible savings that are related to demand and capacity charges, which naturally increase the viability of investment in renewables. On-site renewables is often part of a greater commitment by the companies to sustainability, and many projects seek to get certification as Green Star or Net Zero. And to make it easier and cheaper for our customers, we sought some partnerships in the market with other like-minded companies that we can have a collaborative approach with them. And through these partnerships, we have been working with the Building Excellence Group, which is providing, working closely with design teams and building clients to determine the best sustainable strategy for their projects. And they also provide guidance on requirements, building performance optimization, and green certification solutions. We also work with JRG Energy, Joint Renewable Group. Over there, we focus more on researching, engineering, procuring, construction of utility and mini power plants. And we mostly work in solar, geothermal, and cogeneration space. So just diving into it, the key market drivers for commercial on-site renewables, I've put it in two layers. One is how the world is changing. So I assume everyone heard about Zero Carbon Act, and that it will we will see more than 60% increase in New Zealand's electricity by 2050. That means that there's going to be a massive investment in new renewable electricity infrastructure that will include between 30 to 40 utility scale renewable power plants in New Zealand. We'll have plenty more microgrids and mini grids, and we will see a lot more distributed generation, such as commercial solar and storage. And altogether will increase the resilience of the grid supply and ensure that we have sufficient power capacity that will meet New Zealand's future power demand. We also see younger generation that urge to take action on climate change, and as they come into the workforce, we see a clear preference from them to work for environmentally conscious companies. And as a result, more companies seek to reduce their impact on the environment by changing by adopting their operations and processes, and by sourcing materials through an environmentally certified fair trade supply chains. They reduce waste and they generate their own clean power. Just touching on COVID-19 and our COVID economy, I believe that as a nation, we have successfully navigated COVID-19, and we're now beginning to rebuild our economy. With that, our attention should focus again on how we must mitigate the impacts of climate change on our world. COVID-19's impact on the global economy triggers some uncertainty in the energy markets. A quick example comes to mind is that it is difficult to predict how the drop in the global oil prices is going to affect the manufacturing and the uptake of EVs. Going down from a global and how our world is changing to how that impacts our businesses. So obviously it's an opportune time to shake the old ways of thinking. Solar isn't just for malls and airports anymore. A growing number of businesses have discovered the financial benefits of commercial solar, and they're starting to look at that as a potential revenue stream. They generate good returns on your company's investment. So a property design system that is installed in a commercial space will typically break even between 6 and 10 years. and it will yield between 7 and 12% return on the company's investment, but that is taking into account cash discount and inflation rates and so on. Bank rates for sustainability loans are normally lower than those 7 to 12%, so you can expect additional return for yourself even if you've taken the money from the bank, which is making an on-site renewable work for both your company and the bank. But of course, once having a renewable energy system installed, it's an asset and it adds capital value to your commercial property if it's installed on site. It's important to celebrate your company's commitment to sustainability. Distributed energy is a natural move forward for any sustainable company that has a focus on integrating environmental and economic considerations into every aspect of their business. And again, it goes from the supply chain all the way down to their energy usage. And as I've mentioned, there's a growing number of future buyers from the younger generations that do care deeply about climate change and renewable energy. So it's certainly an opportunity to celebrate and show the world that you care. Businesses have the strength of working, most businesses have the strength of working 9 to 5, which is unlike household, and they tend to use their energy before 9 a.m. and after 5 p.m. That means that businesses use the majority of their businesses between 9 and the majority of their electricity, I'm apologizing, between 9 and 5. And it makes it ideal for solar power systems, making an on-site renewable work for the business, and it reduces the electricity and other operational costs of the business. And as I've mentioned, demand and capacity charges in some occasions. The reducing cost of commercial solar and storage is also a big strength in the industry, and it is just stating that a good quality commercial solar power system costs around $1,600 to $1,900 per kilowatt installed here in New Zealand today. Battery storage costs around $1,800 to $2,200 per kilowatt hour installed. And at the low end of the pricing range, a 30 kilowatt can generate approximately 150 and 120 kilowatt hours a day, which would service a typical shop or a communal areas in an apartment building. And in such a scenario, there's an opportunity for on-site renewables to get close to 80% of the energy generated being self-consumed in the building, and in some cases you can even get 90 or even higher, 90% or even higher of the generated energy used in the building, or as I call it, self-consumption. Maintenance costs of a system can be a strength and a weakness depending the technology that you select. Solar panels and ground source heat pumps are low maintenance. They have very little upkeep costs, and that's unlike wind turbines and hydro turbines that have moving parts, and therefore they're more prone to breakage and they need more servicing. So I chose to share our project methodology with you today because the majority of companies install solar after the building is complete. But with some forward thinking, you can make a solar installation cheaper and a lot more efficient. The decision-making process for generating power on site can be a daunting one. It's time-consuming. Suppliers' quotations can come in very long, thread of pages, and they could be very technical and difficult to compare. They're not always coming apples for apples. I can't say how many times clients told me I couldn't make heads or tails of it, and the project went into a too hard basket just simply because they couldn't really make a decision based on the information that they had at hand. So bringing to your project solar consultant will help your client, will help you or the client to navigate the RFP process, the solar installation, the metering, the monitoring, and all the tax breaks and credits that you can get from installing on-site renewables. The site resource survey is a process where we gather data to identify the renewable resource that can be harnessed on site. Solar radiation, wind speed, and ground temperature data are normally readily available, but they're not always suitable for the specific site. In particular, wind, I would say, should be measured, the wind on site should be measured between 6 and 12 months before you make a decision about wind. In the technology selection, the renewable technology selection, we look at low-cost, high-yield solutions. It is not unusual for us to employ 2 or 3 different renewable technologies at the same time or on the same site. And a good candidate would be a building complex or an office complex that has a gym or maybe a swimming pool, and they have high demand for hot water on one hand and also high demand for electricity. So we can combine solar thermal or geothermal together with photovoltaic to generate both heat and electricity in the same site and harness the best of the resources available. The technical feasibility, the financial viability, and the environmental benefits, we'll go through them in more detail. But our starting point with projects is, as I mentioned, the demand load analysis. We keep to the first rule of on-site renewables. That rule is, before you generate, energy efficiency first. On-site renewable systems should be considered only after the subject building has reduced its overall load as much as possible. This should be done through other building energy efficiency measures so that the maximum potential of on-site renewables can be realized and unnecessary losses can be avoided. By reducing the demand of the building first, the energy demand in the building first, with the least cost measures, the size and the cost of power system can be reduced. It could be as simple as changing your lighting to LED. So do that before you look into generating your own power. The example that you see on the slide here is of a warehouse building owner that is planning to extend the warehouse and wants to investigate solar. The historical data, which is in the orange table, is of the existing building, and we've analyzed that, and based on the usage profile in the warehouse, a demand load forecast was developed, and it is shown in the blue table, and is also presented in a monthly demand forecast in that graph that you see below. Hold on, I'll just get my marker thingy on that graph here. That shows us the minimums and the maximums of the forecasted power demand for the year. I'll turn my camera as well. Sorry about that. The top image on the right is showing a day-by-day load profile, and that is obvious that on the Sundays, the first 3 Sundays, the business did not operate, and in the last week and a half of that month, the business operated or moved into a 24/7 operation. You can see also that most of the energy on a typical day is used during the peak solar hours, which suggests a correlation between the solar energy and their time of demand. We can also identify the electrical base load. Down in this is an hourly graph that looks throughout the year. And the green region over there shows us what is the base load of that building. The blue region shows us what is the average power demand, and the red is the peak power demand. And you can see that anomaly, the green anomaly over here, of how the base load had increased exponentially, and that's an anomaly that we would normally investigate. Sorry, just need to go back to normal. Right. Site renewable resource. We need to decide which resource to utilize. So we look at the solar resource. As I said, DAPA is readily available for most locations in New Zealand, and the more installations that we have installed, they come up with monitoring, and we collect more current data. So that's really great. The wind resource is based on a height of an anemometer, and if your wind turbine hub height is not at the same height, you would likely to need to adjust or amend the data to suit the specific turbine that you're looking for. So it's a lot more specific set of data, and to properly evaluate site wind resource, we recommend at least 12 months worth of measurements. Geothermal resource at the commercial applications level, not at the utility level, uses low-grade heat that is extracted only meters deep from the ground, and is typically used to produce mechanical air and water heating, mostly through a ground-sourced heat pump. The purpose of a ground-source heat pump is to absorb low-grade heat from the ground, exchange that heat with a refrigerant, and that achieves a higher grade heat. We concentrate that heat and store it in a tank and release it for use in space heating or domestic hot water as it needed. Hydrokinetic resource is a big thing, but within the hydrokinetic technologies, what I'm showing in this image is an inline hydro turbine. It is an emerging and innovative technology, and utilizing piped water systems in buildings and water utility infrastructure. Those turbines have an untapped potential to recover energy and to reduce net energy consumption, greenhouse gas emissions, and operating costs. The inline turbines are custom designed, and systems are placed within water networks at key locations. So typically mechanical plant room, which is good for a multi-tenant, multi-building, mixed-use type development, or a retirement village where you have big water mains coming in, so you can actually utilize that infrastructure and generate energy. This system are able to recover energy over the system, the water pressure that flows through them, and they have no negative environmental impacts. So once we've decided what is the best resource to harness on site, we need to select the technology within that resource. For solar, there are several solar technologies, of course, that can be adopted for commercial buildings. Some can generate electricity, some can generate heat, and some co-generate heat, or more likely steam, to produce power. The most common one is photovoltaic, and we'll call them solar panels. And this year they're coming in panel ratings between 300 watts and 500 watts, which is great. Only 10 years ago we were like on 200 and 210 watts. So we are able to see advancements in the technology and the performance of those devices. Building integrated photovoltaic technology is also an advanced technology. I don't want to dive into that too much, but what I would like to mention is notable technology in that sector, which is a low E photovoltaic glass. That type of integrated solar panel comes in a transparent or tinted glass, and it's integrated into a glass curtain wall or a skylight or any glazed surface around the building facade. And it's capable of generating electricity while providing thermal insulation, acoustical insulation, and daylighting control, as it may be required by the architectural building design or the facade design. So that gives us a combination in this technology of both active power generation, but also passive thermal insulation and acoustical insulation that help us reduce energy demand on both sides. And obviously that's an attractive factor for return on investments because most of the energy is self-consumed in the building. When you consider capital expenditure with building integrated photovoltaics, you should consider that against the cost of a facade with and without BIPV to actually have a proper evaluation of the financial viability of an investment. From exercises that we have done here in Auckland with a system lifespan of 30 years, you can achieve a levelized cost of electricity of as low as 7.5 cents per kilowatt hour, which is not too bad for commercial business electricity rate. There's also solar thermal within the solar technologies. We commonly call them solar heating. It's my preferred technology for baseload hot water and swimming pools and some space heating applications, but I'll leave the discussion on solar thermal to Marcos from Apricot Solar. He will be presenting next week about solar thermal, so he'll be pretty good about that. Micro wind turbines, you've seen an image in the previous slide. They are a good visual aspect that can showcase the company's commitment to sustainability and carbon reduction. They're typically rated about 1 kilowatt and the standard size, and it costs about $3,000. So if you do the math, it generates about 1,200 kilowatt hours in a year. But when you look at a scale system of 100 kilowatt, just like in the example below, the cost will be in the order of 2 to 1 when it is compared with solar PV market prices. And you take that cost into account, and you take all the preliminary work on site that you require and the necessary permits. You will see that my statement is with micro wind turbines, either go big or don't go at all. I've mentioned inline hydro, and those are installed in large diameter water pipes. The technology requires careful engineering and its coordination with the water utilities, and to make sure that you don't contaminate fresh water supplies or cause pressure drop. So it's very important to have your designers and installers selected carefully for such projects. But a good fit for technology, as I've mentioned, is a multi-unit development, such as retirement village or shopping centers where they have large pipes as water mains coming into the development. Geothermal, the cost of geothermal are largely incurred upfront. Simply put, it is expensive to carry the seismic sensing, the test well drilling, the confirmation testing, and obtain all the permits and other necessary preliminary investigations to get to that stage and decide, okay, we can go for a geothermal plant. But it is used when you use a ground source heat pump for a communal array, so a very, very large array that is installed in low depth in the ground. You can service offices or apartment buildings and mixed-use developments by using that single communal array and then connect it to smaller distribution units that are located, say, in each office. And they're capable of producing the desired heat, and the user in the office can control it through a thermostat or a timer and get their own power bill. They have very low operating costs because they're very static in terms of taking the heat. It's always available over there underground, that is, and because of that, it's an attractive consideration for social housing and aged care sectors, which are long-term owners, operators of their properties. The standard ground source heat pump needs somewhere between 50 and 80 meters of pipe per kilowatt, or if you coil it, it's about 10 meters in diameter of a coiled pipe. And our rule of thumb is that a standard trench roughly requires twice the floor area of all the levels in your building. So looking into the technical feasibility study, there's some preconditions for commercial solar. The distinct size breaks that we look at them are systems that are less than 30 kilowatts, over 30 kilowatts, and over 100 kilowatts. To put this into context, in New Zealand, the average household in 2019 residential installation was 5 kilowatt, around about 18 to 20 panels. there is a size break of 10 kilowatt within the residential sector, but I won't go into that. Systems that are less than 30 kilowatts generally use the same hardware, and they fall under the same sort of grid connection rules for residential systems. That means that residential system installers can also handle that type of installations, and you don't really need a specialist commercial power gear only in more complex situations. You probably need an independent consultant. But when you go to 30 to 100 kilowatt, the solar arrays of this size, solar arrays of this size require special systems to protect the grid from all the electricity that it can generate. They will need special permissions from your local network authority, Vector, and so on, to connect it to the grid. And a commercial solar specialist like our company is recommended for systems of this size and larger to make sure that you navigate through all the commercial hurdles, as I've mentioned, RFP and design and so on. When you look at over 100 kilowatt systems, these are very large systems. And in addition to the commercial solar design specialist, I also recommend a specialist installer who understands the specific engineering requirements for such big systems. They generally go on large shopping centers or large warehouses where up to 100 kilowatt will go on apartment buildings, smaller stores, and office buildings, and so on. When you connect the commercial solar system to the grid, you need to make sure that you're not getting caught in an export limitation. Basically, as I've mentioned several times, you want to use all your energy, but if you're working 5 days a week, it's inevitable for your business to export some power over the weekends and when you're in downtime. Those mandatory applications should be obtained prior to the commencement of construction. But when you install a 30 kilowatt and up system, it's very important to see in writing the network's approval of the system. Every solar power that connected to the grid must be approved. For larger systems, some approvals come back with conditions like this 90 kilowatt system has been approved, subject to the system having an export limiting device set to 10 kilowatt. Knowing this is very important because it involves cost to add limiting devices and equipment, of course, to meet these conditions. But also export limiting also affects the projected savings. This is where an independent consultant will focus the design on maximizing self-consumption rather than oversizing the system and ending up with an unmanageable power export. Some installers not always factor these costing into their submissions or tenders, mainly because there's a tendency to hold on submitting your network applications only a few weeks before you come to install the system. The issue is that it's normally after the roof is on, so it's in the middle of the project and it becomes a surprise cost to the client. So you want to make sure that you understand that the network conditions for your specific installations are clear to you. You want to obtain a formal copy and approval, and if you need to seek an opinion from an independent person, that's always good. When you're investing, in large solar panel arrays, that involves a fair bit of capital cost, and you want to avoid any nasty surprises from that. Just to throw another layer of bureaucracy into it, resource consents and building consents. Some installations do require resource consent, I should say. So you need to check that with your architect or resource consent specialist if this applies to your building, mainly where it's located. It's also outlined in unitary and district plans, if you are familiar with them. But generally speaking, energy works does not require building consent. That basically Section 3043 of the Building Act. There are some exceptions to that, but really a part of building integrated photovoltaics that form a part of the building envelope. Standard solar panels do not require building consent. Other technologies vary, and we have to look into that at case-by-case basis. The weight of considering in the technical feasibility, the weight of a system on a roof is one of the biggest factors when it comes to installing commercial solar. It is vitally important that a structural engineer certificate is produced and an engineer has physically inspected the site or included in the design sufficient carrying capacity for the solar array. An experienced commercial solar designer is likely to have already the tools and the knowledge to keep the structural engineer's work easy and more affordable. Well, if you have not engaged a designer for your project, be sure that you at least have a detailed roof plan shown to you before the installation, so you know what's going to happen. Just touch very quickly, flat solar panel arrays are generally more common compared with tilt installations. They are more cost effective and they can be altered to suit any variations on the roof in the last minute easily, which is not the case with tilt frames. That also add additional weight. They have wind or pull load, and they also another balance of material costs. Ground-mounted systems are a very good option if the roof is not suitable, but they are sort of a bit of a niche in the commercial installations, and they require more civil and infrastructure planning, and of course cost compared to a readily available and unused rooftop installation. The example in this slide illustrates an apartment building with a rooftop solar on a pitched frame. The proposed system and the summary over there, you can see it's a 97.28 kilowatt peak, and it's estimated to generate about 18.6% out of the annual power demand for that building. The dark image over there is an irradiation image. It shows us where irradiation is available and how we see shade between obstacles, from obstacles, and how it impacts on the array. It allows us to space the arrays accordingly, specifically to the site, and so on. This is relatively a simple shade analysis, and where we require it, we can produce a shade model for every hour of the year. It doesn't matter if it's a tree, a building, or near lift shaft. In our modeling, we also apply cloud index to simulate more realistic results to what's going on. And below that image, you have a summary that is showing the energy production and the consumption in the building. As you can see, almost 100% of the power generated on the site was consumed in the building, and it's shown why the bar graph. It shows why on that bar graph. The green area is the generation area, and you can see that it's well below the orange bars, which are the demand load bars. Once looking at a financial business case, once a feasible system option is selected, or several options are selected, they qualify to a financial analysis, and we begin developing the financial model. We're starting from the project capex and the annualized costs. The input parameters that we use include cash discount rate, electricity inflation rates, and if needed, a loan interest or a PPA rate or something like that. The example in this slide that you see is of an off-grid system for a farm store in a remote location. The majority of the capital here is spent on batteries, and the majority of the operating costs is spent on diesel for the backup generator. And then you have a midlife replacement, mainly for batteries and inverters. And these parameters are used to evaluate each proposed case. And then we compare each of these cases in the model to a best case, which would be a grid only, or in this off-grid situation, a generator only. and sort them by order of profitability. So this slide is an example that shows the most preferred option. As I said, we compare the economics, and the parameters that we've entered as costs are used to evaluate the proposed cases. And as you can see, this one is the most preferred option. The investment trajectory in renewables typically spans over 25 years, and the economics of a project is evaluated by the capital investment in the renewables, a comparison of the landlord's operational expenses with and without renewables. In this slide, we can see that the net present cost was $928,000 for an investment of $693,000. The annual worth resulting from that is $65,000. The levelized cost of electricity, LCOE, is a matrix that calculates the present value of the total life cycle costs, including the capital investment. In other words, it tells us what is the cost of electricity generated on site from the solar power of the renewable power system. When we compare it with the cost of procuring electricity from the grid, we can determine if an investment is profitable or not. It also allows the comparison of different technologies. So if we wanted to put wind and solar or different products for different lifespans or project sizes or different capital costs or different returns, that matrix gives us a very good indication what's profitable and what's not. Also want to mention the IRR, or internal rate of return. I consider that a better matrix than the ROI simply because the capital that you invest in an on-site renewable system is essentially used because it's a used asset after its 25 years lifetime. So the return on that investment means that you've also consumed or also used the money that you've invested. You can see the variance in bills on the right-hand side and how the system cash flow would look between a proposed case and the base case. I want to talk about financing renewable projects. Talk about cash or capital expense. Technically, this is not finance, but it's still a common way to purchase a system. The cash price for a solar system will always be the lowest. It's always leading to the shortest payback times and the highest yields because fees and charges involved with finance and leasing are not considered as a part of the system. Power purchase agreements are a type of leasing agreement. Essentially, in their most fundamental format. The core idea is that a third-party energy retailer installs and owns the system on your property, which means they own it and they're legally obligated to operate and maintain it, and they're committed to keep their uptime as much as possible. And you enter into an agreement, you enter a business into an agreement to buy a set amount of electricity over the agreement time frame, which is normally long term. It can be anywhere from 7 to 20 years. The main benefits are that your electricity costs overall are lower because the price of electricity under a PPA will always be cheaper than what you can currently purchase. Not always, but mostly will be cheaper than what you can currently pay your common electricity retailer. And also that there is no upfront costs for installing the system, so that makes a lot more cash flow available. The downside is that it may also affect your business debt ceiling because a PPA, like a lease contract, is increasing your company's financial liabilities for the duration of your contract. Because self-consumed solar energy is far more valuable than energy being exported to the grid, if you're considering a power purchase agreement, it is very important to have a system that is fully optimized and sized for maximum self-consumption. PPAs set out the price of solar energy for the duration of the PPA when you get into a contract with them. So while you might have a low price for year one, it's important to read the fine print and see how that price will be adjusted over time. The best PPA is that fix the prices and there's no changes, but in reality, you want to see the lowest change in your electricity rate over time or none at all. Green project loans. The business and green loans, green loans will allow you to negotiate pricing with the solar installer as if you were a cash buyer. If the savings from a new commercial system are more than what you pay for the interest on your loan, you can see why it would be a no-brainer option to avoid taking a big cash flow hit and using the cash or the capital expense of your own to buy a solar system. Basically, you earn less, but the money costs you nothing. In most cases of green project loans, the banks are mostly adjusting their interest in green projects loans to allow you to have your own profit from that investment as well. Engineering. A system design package normally includes detailed drawings that are suitable for tender or for contractor pricing. At a commercial level, it is of very high importance to ensure that there are no clashes between the building services and the structure design as taking the renewable installation into account. For example, if the installation of a solar carport could be coordinated with the civil infrastructure to avoid overhead or to avoid clashes really with overheads or underground cable installations. You need to integrate with your building services properly. Bringing a renewable energy consultant to your project to work with the mechanical and the electrical building services during the design stages is an important thing, and it can influence the building design. In early design stages, we can detect roof level shading obstacles such as condensers or vents and account for the cable installation management like cable trays, make sure you get space in service risers, room for your switchboards, data connections for monitoring, connecting the system to the fire alarm system, and so much more. If your building is also if you're coming at the end of the project and get your solar contractor to do that work for you, you're putting them in a situation that it's hard for them to deliver good quality workmanship because all the other spaces were not taking their works into account. So they always have to install cables on the surface or not in a tidy way and try and find new places for their switchgear and so on. So it's worthwhile putting the time into designing it correctly. If your building is also pursuing a Green Star, Net Zero, or similar certification, you also need to demonstrate the emission reductions from your on-site renewables to achieve the targeted scores in the specific certification framework. And then there's also the methods of safety in design, peer reviews, and independent technical tender bid evaluation. I won't touch renewables with embedded networks because we're losing time, but I would say that it's a good thing to have. If you have an embedded network or a customer network, you can actually enjoy the ability of selling the on-site generated electricity to the people connected in the embedded network and create a revenue stream. The industry from a procurement perspective is changing really quickly, and we see so many new technologies coming out. As I mentioned, this year we're seeing solar panels technologies that come in 445 watts and 500 watt panels coming into the commercial market. Module level monitoring is very important. It allows you to do a lot more things and reduce your your installation costs. You can install longer strings, that means less cables. It gives you module level monitoring. You can see exactly what happens. So it reduces maintenance costs and power plant downtime. and most importantly, it can generate 10 to 12% more power than a standard string inverter under standard conditions. You also have smart solar inverters coming into the market, and there are designed to either switch electric vehicle charging stations or common building services as a priority to servicing other loads that are less important. We also see hybrid solar inverters that allow us to operate as a grid-connected system during normal times, but as a backup power system during outages. For that, you're going to need to have some storage. So if we talk about storage, it's one of the biggest challenges in the energy world, and that level of technology. And there's a lot of advancements happening in the world. But since the rise of the EV markets, more lithium batteries are reducing costs and improving efficiency. But there are some other technologies like supercapacitors that are more suitable for businesses that might have a lot of forklifts or motors, and flow batteries or vanadium batteries that is for companies that have very large demand or very high demand for energy, and it is a continuous energy demand, more like an industrial sort of platform. You want to think about your supply chain and ensure that you work with a fair trade suppliers when you buy the gear for the plant, especially if we're talking about batteries. There's the discussion around the world with cobalt mining and how it's been using child workers for mining in the Congo Republic. So companies like Sony and Panasonic have already engaged with tracking the supply chains to prevent such things from happening. The construction of a system should be undertaken by a commercially skilled installer, and it could be challenging because there's so many projects that you need to make sure that you have the right power rating, and a different number of panels can be coming in from different construction companies or contractors. So don't follow any advice. Just buy the system that you want, not what they have. Determine the size, the rating of the rating and the architecture of the renewable power system, and that should be enough if you base it on the power demand and the energy consumption forecast of that is forecasted for the project or for the building. And if you're getting an installer to design your system, make sure that the system and the components are not oversized or undersized in respect to your demand load. Submissions from when you go through selecting a contractor, submissions can be often very technical, and it makes very hard to make a decision who will be the right contractor for you. So it's always worthwhile to get a specialist advice that will help you sift through this RFP process. Inspections, we recommend getting your consultant to complete 3 inspections: roof level works, plant works, and system commissionings. These normally occur in different construction stages, and they give the consultant an opportunity to communicate inspection items to the contractors early enough in the process. An example that I can think about is that the solar installer often use the construction scaffold, but if there's an inspection item that they need to attend to and they're not informed in time, they can come back and the scaffold is down, the work will be slower and probably not very tidy. Also, practical completion certificates are requested for many projects to be included with the project final code compliance certificate application. Because the installer is required to issue a compliance certificate for their completed work, it is not reasonable for the same installer to issue an inspection certification of his own work. So a practical completion certificate is basically the cover page for a detailed inspection of the installation and the plant, to confirm to the client and to the authority that is looking at that the project is complete. And if the project contract includes retention for the duration of the defects liability period, the practical completion date is normally the date from which the final payment, retention, and defect liability periods begin, and that sort of protects the client. Very briefly, because we're out of time, I'll talk about monitoring, operating, and maintenance. Operating system O&M for up to 100 kilowatt systems is ranging between $10 and $17 a year per kilowatt, and it's dropping down with scale. But you can reduce 85% of your operational costs by getting your company staff to be involved. You can have visual inspections to look for signs of animals, nest, cables that might have been chewed on. And then you want to have some trained staff, like a maintenance staff or something like that, that can actually go up on the roof and have a visual inspection to see if they see anything loose, grazing, rusty brackets or frames and cables that are exposed to direct UV light. And you obviously can have some trained staff that is sitting there on the desktop and having the system monitored so they can see if any alerts or downtimes are coming. They can report, they can produce monthly reports so you can track your investment. But ultimately, maintenance activity must be performed by a qualified electrician that is trained to work on heights and with live conductors and direct current voltages that are present in PV systems. 5033 standard provides a checklist that covers the faults, repair, and periodical maintenance that is typically required to be carried out by a qualified PV installer or a technician. And we certainly recommend to our client to sign an ongoing maintenance agreement with a qualified technician to ensure minimum planned downtime, and they also tend to give you a prompt when the service time is due. Well, I hope the presentation was interesting and not too stretchy, and I'm happy to take any questions if you have any more time. And thank you, Mike. I'll turn the presentation off.
Thanks, Yariv. That was excellent. Highly informative, I thought.
Thank you.
Well, yes, we do have lots of questions. We had quite a few coming in as the session was going through. And what I'm going to do is open up the microphones for people so they can ask them in person.
Sure.
Just a quick word before we do that. Time isn't a particular issue. I'm sure with this series of questions, people will be interested in the question themselves and the response. The system will not cut itself off automatically at 5 o'clock, so we can actually answer the questions in full and do well with them. Now, the other thing I'm going to ask is that the questioner introduces themselves, because while we know who you are quite often, the rest of the audience will not, and we've got 100 people here attending today, more than that in fact. So if you could just introduce yourselves, please, before putting your question. And I'm going to go through them in the order that we received them. The first of them is from Terry. Now, we know you're in Carpety, Terry, but if you'd like to introduce yourself, please, I'm going to open your microphone now, so you are available to speak. And your question, please, Terry.
Thank you. Hi, I'm Terry Crichton. I'm the Senior Advisor, Sustainability and Resilience at Kapiti Coast District Council. I just had the thought in response to your statement about electricity demand profiles matching solar PV supply profiles for most businesses. And while I agree that's generally true, we have a couple of facilities where that isn't true. And one of them is obviously our wastewater treatment plant, which runs 24/7, and our indoor pools, which run till about 10 o'clock at night. So I was just wondering what the recommendation would be in those situations. Do you recommend just having solar PV to take out the load in the middle part of the day, designing it so you don't export too much to the grid, and then just having it backed up by the grid for those other hours?
Thanks, good question. Where we see a continuous demand that is fairly consistent, like in wastewater treatment, we try to think of more than one technology, one that is more continuous and reliable. For example, I've mentioned inline turbines. So in a wastewater system, there'll be a lot of running water that needs to be treated. So if you check in a couple of turbines over there, you can generate a good amount of power with very little environmental impact or operational impact. Solar can also be coupled with storage systems. It's a cost-benefit exercise. I've mentioned there's several new technologies that make the cost-benefit equation a lot more attractive. If we're looking at such a large demand like an industrial situation, I'll probably start looking into flow batteries that could generate more power, but they come in a container size device. And they allow you to both have long life of the battery, literally infinite, or theoretically, and make sure that you are capable of harvesting enough energy throughout the peak solar hours to charge the batteries to service you in the downtime of the solar. I hope that answers.
Yeah, no, that's interesting. Thank you.
Good.
Okay, thanks for that, Terry. The next question is coming in from Gohar. So, Gohar, if you'd like to introduce yourself and ask a question, please.
Hi, first, I'm Gohar from University of Auckland, and thanks for your nice presentation. It was really useful. I'm wondering if your focus is mainly on PV panels, or how about solar collectors, solar thermal collectors, and then using another storage for the heat or cool or cooling energy?
Well, our focus is really to find fit-for-purpose systems that offer the best cost-benefit value to our clients. So we don't look into that question in the respect of, okay, we have to go solar thermal, or we have to go photovoltaic, or we have to go wind. We look at how we can mix those technologies together. I've mentioned this matrix called LCOE, which is the levelized cost of electricity. When we do our modeling, we know how much energy is required for the building, and we plug in the different systems. We construct the different type technologies that could generate that energy, and we get a price on it. And then we can find out what would be the cost of energy that is generated from each of those systems, and then see which is the lowest, and that would give us the indication of which one is the most profitable and probably the most suitable for the project. And then we also have to look at the physical constraints. You might find that you've got a very appealing business case, but the technical feasibility of installing such a system might not be suitable for a project or a development. So it also comes down to what stage of the project you are at. If you are at an advanced stage of the project and you've already sort of built your superstructure or your foundations, it'll be very hard to come in and put a ground source heat pump, for example. Is that answering?
Yes, thank you.
Yeah.
Okay, thanks, Gohar. Next on the line, we have Paul. Paul, if you'd like to introduce yourself and ask your questions, please.
Yeah, hi, I'm Paul from Brackle. I'm the Process Engineering and Energy Team Leader at New Zealand Steel, so we consume a lot of energy, probably about 23 PJs a year.
Yeah.
And we run about 60% cogeneration on our site. Look, I was not jumping to the first question. I'll just go off because I had a question related to what Terry was asking. So in terms of batteries, are you tracking, like in flow cell batteries, what the cost per kilowatt hour is dropping down to? Because it used to be fairly high for vanadium flow cell batteries, and over the last 10, 15 years, it's been slowly coming down. Is that flattening out in terms of the cost for flow cell batteries these days?
We're still a few miles away from that. We haven't had that. Well, it's a commercialized product now, but we haven't had enough opportunities to install them and to demonstrate how financially they could be reduced. So it's a matter of manufacturing volume, I would imagine. So we simply don't have enough of those. But let's say that your factory was located in Northland, then the cost of electricity over there would be a lot higher. Even if you're using cogeneration, you're still going to have a demand for power, and storing that energy would probably be cheaper as a financial equation than procuring it from the grid over there. In a nutshell, I can say that a vanadium flow battery would probably have a tech cost of somewhere in the order of 22 to 25 cents per kilowatt hour. But I think these days it's a little bit lower. Last time I looked at it was about 6 months ago.
Yeah, I haven't looked at it the last couple of years. It was still cost prohibitive when I did. Okay. The other thing that I was quite interested in, and I've seen some drainage systems, which was about the hydrokinetic. You know, if you've got a lot of wastewater, yeah, particularly if you've got a bit of head behind it too, that's a bit useful. But I was quite curious because it also looks quite inefficient in some ways, because you've got the municipality, you know, generating using a lot of power to develop head to supply it to a customer, and then you actually taking out using that head and flow to generate power at the end. I'm just wondering, in terms of what pressure loss though you were, if you had some curves in terms of which systems were more efficient than others, if you in terms of some of these hydrokinetic, or have they got down to a pretty standard design? I'm not too familiar with these hydrokinetic generators at the back end of a system.
Right. Again, good question. Yeah, I think there's an untapped potential to use inline turbines. Their impact on pressure drop is, as far as I understand, is negligent. I have not seen any curves that suggested otherwise. And they can work from standard piping systems at 200 kPa, so you don't really need to spend a lot of fortune to get to high pressure, up to a much higher level of pressure and flow rate. And the bigger the pipe, the more pressure, the more velocity you'll have in your water, and the more energy you could generate from that. So it's a fairly neutral process. You're just putting an impeller inside the water pipe or tapped onto the outside of the water pipe, and it doesn't really cause a lot of turbulence. But it does require careful design. There are some off-the-shelf products that I can share with you if I'll get your email later on, and you'll be able to see a whole range of them. And they can work from 1 kilowatt through to about 70 or 80 kilowatt per turbine, depending how big you go.
Okay. All right. Be interesting to see what the cost of those are involved. And then the other question was on a different,
Yeah.
And the other thing was more on also, you know, you talked about ground source heat pumps and so on.
Yeah.
What sort of temperature gradient, what sort of data do you need for a temperature gradient, or are you using just fairly standard models and knowing what's in the particular areas? Because, you know, there's a wide range of strata around in New Zealand. It's, you know, just from where we are, we're on the edge of a couple of plates, and
average ground temperature about 7 meter to 8 meter deep, which is your standard small commercial foundation depth, would be around 15 to 17 degrees from our measurements in the past. But I must admit, it's only measured in the Central and Upper North Island. I've never been involved in any geothermal project in the South Island, so I can't really express anything over there. But obtaining a 15 degrees centigrade is not that hard for most locations. And if we have a good bedding area, then we certainly can get quite a uniform layer of 15 degrees heat that can then be exchanged with a refrigerant that will certainly boil at that temperature and will become useful heat for your processes, mainly mechanical.
Okay. All right. Thank you very much. Good presentation. Cheers.
Good. Thank you.
Thank you. The next question is from Alex. Alex was with us yesterday doing a webinar, actually. but I just opened up your mic there, Alex, so you can ask your questions, please, and introduce yourself first, if that's okay.
Yeah, thank you, Mike. Thank you, Arif, for really nice presentation. I am Alex from Lumen. I'm an energy and carbon consultant working in that energy efficiency industry. My question is basically about two. So on the first one is on the micro wind turbine.
Yeah.
Basically, I just want to understand whether we can actually install them on existing buildings. If there is anything like that possible at all, and also what would be the typical capital cost per kilowatt? What would we also require any council permit to do so? And then the last one on that is basically whether do we have any demonstration project that's been done in New Zealand at that level? Yeah, if you can answer this one, and I'll go to the next one.
So micro wind turbines have not had a great success in New Zealand installations. I have to start with that, and I also finished my notes about that is with you either go big or don't go at all. And the reason for it is a part of really making a company statement for something that is visual on the building. You have much better ways to generate electricity, or not much better ways, but on-site renewables through solar, if that's feasible, will be costing about half in comparison to the energy generated from a wind turbine, a micro wind turbine. The cost is not crazy, but as I said, it's still double. It's about $3,000 per 1 kilowatt turbine. Or it's about $1,500 or $1,600 for a photovoltaic, as I've mentioned, per kilowatt installed. And that's why one of the reasons why you don't see it. Building consent you don't need. Resource consent, 9 times out of 10 you probably will need that. It really depends where your building is located. If your building is located in, say, Auckland, Devonport, near a volcanic shaft, then you'll have to comply with the unitary plan resource consent conditions. In terms of successful installations that we can share here in New Zealand, unfortunately, as I said, I know that this is an existing technology, but I do think that they have room on in locations where you don't really have access to harness any other renewable resource like solar or water. You find it a lot on little boats and things like that. So I don't really have a very successful project to show here in New Zealand on micro wind turbines, unfortunately.
Okay, that's all good. My idea was basically if we can actually couple them together with solar PV being covering the nice shiny days in summer, and while the micro wind turbines would cover really bad windy and shitty winter periods, basically.
Yeah,
that was the idea, but yeah, that's fine. My next question is
with you, Alex. On the same idea with you, but turns out that even though a wind turbine theoretically can operate for 24/7 at a set wind speed, when you look at the economics of it, the micro wind turbines don't really address the cost-benefit equations when compared with other resources.
Okay. The other one is just maybe a simple question. In my recent experience about solar PVs, mostly 20 years of life has been considered. Those people I have contacted said 20 years of life is fair and appropriate thing to consider. However, I just noticed that you mentioned about 25 years being presented here. Yeah. Is there any update in terms of the lifespan of those solar PVs nowadays?
It's a very good question, Alex. We design technical feasibility, or we make our technical feasibility selections based on project lifespan. When we do financial modeling, we put the project lifespan about 20 years. When we do physical modeling or technical modeling, we do lifespan of the life cycle of the technology we employ. So if it's a photovoltaic, you can get performance guarantee from the manufacturers for up to 25 years. So it helps us predict quite reliably what the energy production will be in the next quarter of century. If it's a building integrated photovoltaics, we'll actually claim to have a 30-year life cycle or even more, because it's very it's a critical part of your building envelope, and you don't want to replace your whole facade too often. So it really comes down, as I said, to the type of technology and whether we're doing a financial modeling or a technical modeling.
Yep, that's a very good answer. And also, just my last question in relation to that is, what sort of efficiency deterioration we would see in those years for solar PV?
Most manufacturers would state that their efficiency will not drop below 80% in the course of a 25-year cycle than their original plate value or plate rating. So it's about 0.5% per year. But with some manufacturers, you see degradation that is sort of in the first couple of years, it really plummets by about 6-7% and then sort of flattens. Other manufacturers guarantee more linear and gradual deterioration in performance.
Sweet. Thank you, Arif. That's the questions for me.
Okay, thanks, Alex. We do have a couple more questions. Unfortunately, Manoj, who is actually posing both of these questions, or asking both these questions, has had to leave. He had to dash off. But I'll relay them on his behalf, if that's all right, just to make sure that everybody gets to hear the answers.
Sure.
So a couple of quick questions. Any rule of thumb for specific solar PV weights per square meter of roof space? And the second question is, do you have any comments about the loss of efficiency over the period of a month when we have in NZ particularly high humidity rates?
Sorry, the last question, loss of efficiency?
Because of high humidity.
In photovoltaics?
Yes.
Yeah. Okay. I'll start with the last one. The efficiency due to humidity is taken into account in our consideration. When we do modeling, we look at temperature and humidity levels, and we enter a data file that accounts for humidity that has been recorded in the last 10 or 15 years for the location. So in general, yes, we take that into account. We don't see a lot of degradation, and it's normally comes into effect in temperature due to deposits of water droplets on the solar panels or something like that. But I don't have a specific answer in terms of measuring the efficiency drop for humidity only. And the first question was again?
It was rules of thumb regarding weight.
The rule of thumb regarding mounting systems, if you're installing solar panels flat on the roof, depending the racking system that you use, a standard racking system with rails and clamps will probably be about, with the solar panels, you should allow about 15 to 16 kilograms per square meter, or 160 kPa. And if you're looking higher, like a pitched frame or something like that, then your loading will be probably grow to about 20 to 21 kilograms per square meter.
Okay, thanks very much.
One more note about that. If you're using a ballast system, which is typical for flat roofs on membranes, and they use concrete pavers typically to hold the system interlocked onto the roof, the system is essentially floating on the roof, but the loading is very, very important, and the design of ballast system is very crucial to make sure that you don't find the system falling down into the lobby.
Good thinking. I like that kind of logic. It works terribly well. So I don't see any more questions.
Good.
So good. I thought you handled them exceptionally well. Yeah.
There's enough people that have been listening, so I'm pretty pleased, I think.
Good. So it falls to me, of course, to say thank you very much indeed.
Thank you very much, Mike.
It was highly informative. The subject matter, of course, is incredibly interesting. And we know that simply because we had, let's say, nearly 200 registrations today. Yeah. So that was excellent. Thanks on behalf of the attendees. Thank you, the attendees, for coming along and listening to Yariv. I hope you learned a lot. I certainly did. A couple of points from me as just to wind up. A reminder that we have a couple more webinars next week. One that is a follow-on from this one, which is looking at sustainable solutions for heat requirements in commercial buildings. That's with Marcus of Apricus. And we have as well Jack Young talking about compressed air systems. That'll be on Monday. And as you should have seen now, a reminder as well that registrations are now open for our conference, which is being held on the 9th, 10th and 11th of June. An exciting lineup. I was preparing earlier this afternoon a press release to announce some of the speakers on that. I won't preempt the press release, so keep an eye out for it. And we'll be mentioning those in our newsletter on Friday as well, of course. But just once again, thanks, Yariv. Thanks, everyone who is still with us. We still have a lot of people with us, actually. So we'll hopefully see you all next week, and we'll see you in June as well for the conference. Yeah. So for the moment, it's goodbye from us, and have a lovely evening. Thank you all.
Bye.